This lecture is about capacitors and RC circuits. The simplest kind of capacitor we've talked about, it's a parallel plate capacitor. It has an approximately uniform electric field inside. Towards the edges you get edge effects, so it's not perfectly uniform. The charges are equal and opposite. The charge on one side is called plus Q. The charge on the other side is then minus Q. These are the total charges plus Q in the whole positively charged plate and in the whole negatively charged plate. Due to these charges, there's some voltage difference, V, across the two plates. And the more charge you have, the more the voltage difference is. The constant of proportionality, C, is called the capacitance. Now, if we connect the two sides of the capacitor with a resistor, resistance R, what we have now is an RC circuit. And what's going to happen is all these positive charges that want to get away from each other are going to flow through the wire and through the resistor to the negative side, to the negative charges that they're attracted to. So this is going to create some current, I. Now I'm going to define the current going in this direction, and that's going to mean that the current's going to be negative. But I'm doing it this way because it makes it a little bit cleaner with the negative sign later on. Now, because the voltage is proportional to the charge, as the charge is drained from one side of the capacitor and flows to the other side, the voltage becomes less and less. And that means that as more charge is drained, essentially it's not being pushed away quite as hard. And this means that the current's going to become less and less. So initially the current's going to be flowing quickly, but as the capacitor drains, there's going to be less force pushing the current around, that is less voltage, and so the capacitor is going to drain at a slower and slower rate. What this means ultimately is that the current is going to asymptotically approach zero. So now that we see that intuitively, let's apply Kirchhoff's laws to the circuit. Kirchhoff's law for voltages will just tell us that the voltage across the resistor is equal to minus the voltage across the capacitor. Now that minus sign appeared because of the way we chose the direction of the current. Plugging in Ohm's law, we get IR for the voltage across the resistor. And plugging in this formula for capacitors, solving for V, we get that V across capacitor is just Q over C. So I replace the voltage across the capacitor with Q over C. Now let's note over here on the left side that the current is the rate of change of the charge. Okay, current, amps, is coulombs per second. So current is just the number of coulombs per second going into the capacitor here. Now this is why I defined the current this way before, because I wanted current to be the number of coulombs per second going into the capacitor, so that current would be the rate of change in the charge. If I had defined current going the other way, current would be minus the rate of change in the charge, because current would be the rate at which charge is being drained from the capacitor. So I just didn't want a minus sign here, and I got it there instead. It doesn't matter which way you do it, though, as long as you're consistent. So plugging that expression in for I, and moving the R down to the other side, we get that the rate of change in the charge is equal to minus 1 over RC times the charge. Let's think about this intuitively for a second. This is what we had discussed before. The charge, the presence of this charge pushes current through the wire, thereby decreasing the charge. But the rate at which the charge decreases becomes less and less, because the more charge flows out, the less electric force there is pushing the charge out. That is, as charge flows out, the voltage becomes less and less, so it's not pushing the current through quite as hard. So that's what we found here. As the charge becomes less, the rate at which the charge decreases also becomes less. Note that because of the minus sign, it is a decrease in charge. If charge is positive, then the rate of change of charge is negative, meaning that charge is decreasing. Now this equation, it describes a rate of change in the charge that's proportional to the charge itself. And if you remember from a calculus or differential equations class, the function that does that is an exponential function. In this case, because of the minus sign, it's exponential decay, and that's going to have the this property of asymptotic decay that we talked about earlier from an intuitive perspective. Here we've got the same thing from an analytic perspective. Now this variable lambda, this is called the decay constant, and it is equal to, if you remember your calculus, you can substitute this into here and find that lambda is equal to 1 over RC. You can also guess that from dimensional analysis. Okay, lambda has to have units of 1 over time so that the argument to the exponential function is unitless. And the only way you can take these properties of the circuit, R and C, and combine them in a way that has units 1 over time is to use 1 over RC, because that will have units of time. So if you ever forget how the decay constant relates to the resistance and the capacitance, you can use dimensional analysis to figure it out. So lambda, the decay constant for the circuit, is equal to 1 over RC. Okay, so let's do some graphs of this. So plotting the charge on the capacitor with respect to time, the pattern we're going to see is exponential decay. It's going to start out with an initial value, Q naught. Note, if I substitute t equals 0 into this, I get e to the 0, which is just 1. So at t equals 0, the charge is just Q naught. So we start at Q naught. This is the initial value of the charge. And then as t increases, because of this minus sign, it becomes exponentially less and less. Never quite reaches 0, it just asymptotically approaches 0. The larger lambda is, the more rapidly the charge decays towards 0. And that means that if the resistance is smaller or the capacitance is smaller, because lambda is 1 over RC, so as these get smaller, lambda gets bigger. So as these get smaller, also we get a faster decay. And this makes sense intuitively. Okay, if the resistance is small, that means that current can flow more rapidly. If the capacitance is small, that just means there's going to be less charge actually accumulated here, so it doesn't take as long to get rid of it. Note that we could divide both sides of this equation by the capacitance C, and that would give us that the voltage across the capacitor also decays exponentially. We could use Kirchhoff's law to replace the voltage across the capacitor with the voltage across the resistor. Recall, voltage across the resistor is just minus the voltage across the capacitor. The minus sign cancels out on each side. Whoops, I forgot the little initial symbol here, VR naught. So also the voltage across the resistor decays exponentially. We can then use Ohm's law and cancel out the resistance to find that the current through the circuit also decays exponentially. So whether it's the charge on the capacitor, the voltage on the capacitor, or the resistor, or the current in the circuit, they all decay exponentially. So this is a basic characteristic of RC circuits. Brief digression about the units of capacitance. If we solve for capacitance, it's Q over V. This is from this defining equation for capacitors, Q equals CV. And while Q over V, Q is in coulombs, voltage is a joule per coulomb. So this is some number of coulombs squared per joule, and the shorthand for this just written as F, and that stands for farads. So the units of capacitance is coulomb squared per joule. You can also call it a farad for short. Okay, let's do a sample problem. Here's an RC circuit. This is the symbol for capacitors within an RC circuit. Be careful not to, well, capacitors in general. Be careful not to confuse it with the symbol for battery, which looks similar, but one line is shorter than the other one. And let's have a capacitance of 400 microfarads, a resistance of 1 megaohm, and an initial voltage of 1.5 volts. And let's ask the question, how long does it take for the voltage to drop down to 0.5 volts? So let's take our exponential decay equation for the voltage. We can replace the decay constant with 1 over RC, because that's true for all RC circuits. We're solving for t, so let's start trying to isolate it. We'll start by moving the V naught over to the other side. Now let's take the natural logarithm of both sides, because the logarithm is the inverse of the exponential function. So this gets rid of the exponential function. And now we can just move the minus sign in the RC over to the other side to solve for t. Let's put in numbers. RC is equal to 400 seconds, and V over V naught is 1/3, so natural log of 1/3. I forgot about the minus sign. Note that the natural log of 1/3 is negative, so that cancels the minus sign and makes the answers positive. And I find that the answer comes out to about 440 seconds. So it takes a few minutes for this capacitor to drain down to 1/3 of its original value, original voltage. So for homework problem 1, a similar problem. We have an RC circuit, capacitance of 10 millifarads, resistance of 2000 ohms, initial voltage of 10 volts. What will the voltage be after 1 minute elapses? Now let's talk in a little bit more detail about the physical properties of an actual parallel plate capacitor. So here's a parallel plate capacitor. I'm trying to draw two parallel circular plates. It took me so many tries to get this to look right, get the two circles to kind of match each other a little bit. They have an area of A and a distance between them of D. Now we know that the electric field between them is approximately uniform for a parallel plate capacitor. And this means that the voltage across the capacitor is equal to the strength of that electric field times the distance between the two plates. Now what is the electric field? It might be somewhat intuitive, but the electric field is proportional not just to the charge, but to the charge density. That is the charge divided by the area density of the charge. So if you have some charge, more charge results in more electric field, yes, but also concentrating that charge onto a smaller area plate also strengthens the electric field, whereas distributing it over a really big plate would weaken the electric field. Now, the proportionality constant happens to be something called epsilon naught, and epsilon naught is called the permittivity of free space. Now, epsilon naught might seem like something new, but it's actually not. It's a constant that was hiding in the definition of K. That is K from Coulomb's law, which was 9 times 10 to the 9th in standard international units. K is actually equal to 1 over 4 pi epsilon naught. It's really just a more convenient way to write the quantity 1 over 4 pi epsilon naught, which comes up a lot. So you know K, and that means you know the value of epsilon naught. Epsilon naught is just 1 over 4 pi K. Now plugging this expression for the electric field into this equation for the voltage, we get that the voltage is epsilon naught QD over A, and solving this for Q, we get that Q is 1 over epsilon naught A over D times the voltage. Now recall the definition for capacitance. It's Q equals CV. So this quantity here is the capacitance of a simple parallel plate capacitor. So this means that if you want to have more capacitance, then there are a few things that you can do. One is increase the area. More capacitance. Increase the area of your plates. You can also decrease the distance between them. Get the plates really close to each other. And actually, you can decrease the effective value of epsilon naught. Because epsilon naught was the permittivity of free space, but you don't have to have free space in between the capacitors. You can have some insulating material that's called a dielectric, and the dielectric actually has a lower permittivity than free space. So this then becomes not epsilon naught, but just epsilon, where epsilon is called the dielectric constant, and it's different depending on what your dielectric is. And by having a lower dielectric constant, you can actually increase your capacitance. So lots of area is what you want. You want the plates to be very close together, and you want some dielectric with a low permittivity in between them, and that's how you can get a lot of capacitance. Now this motivates a certain design for capacitor called a multi-layer ceramic chip capacitor, or MLCC for short. MLCC capacitor, I guess, multi-layer ceramic chip capacitor. And the basic design is that on the two sides of the capacitor, instead of just having two simple parallel plates, you have a series of plates, and I've drawn the two sides in orange and blue to distinguish between them. You have a series of plates that are sort of interleaved like this. So because you have many plates, in this particular drawing I've got 4 plates on each side, that's effectively a lot more surface area because each plate has some surface area. And also D is really tiny because it's this tiny little separation here in between the plates. So you get a tiny D, you get tons of area, and that gives you plenty of capacitance. And then the space in between is filled with ceramic, which I've decided should be green for some reason. And that ceramic is the dielectric. It has a dielectric constant, or permittivity, lower than that of free space, and so that helps increase the overall capacitance. Of course, it's also insulating, so the capacitor is not just shorted right out. Now, what these actually look like when they're on a printed circuit board is something like this. They're usually about 1 millimeter in size, and but they can be smaller or bigger. And this whole middle section, what you see here is you see the ceramic, which has a kind of orangey brown color, something like this. And the two ends are soldered down, so they'll have kind of a silvery gray color from that tin, usually, or tin lead solder. And one of my internships when I was in college was actually that these ceramic chip capacitors, a lot of them were being found to have some cracks after they were installed. And my job was to try and figure out why these cracks were forming. And one idea we had was that maybe it was from when the capacitor is soldered down to the PCB, it gets really hot over here, and this creates a thermal gradient that could result in cracking, kind of like if you take a ceramic bowl, right, that's at boiling temperature, say, and then you go stick it in the snow, it could crack or break due to just the thermal shock, the thermal expansion and contraction. So that was one of the explanations we were looking at. What I found was it seemed like actually only some capacitors would crack as a result of the thermal shock. So maybe what was going on was a small number of the capacitors had a tiny little pre-existing crack, and then when you soldered it, the thermal shock would cause that pre-existing small crack to propagate and turn into a big crack. But most did not have the pre-existing cracks, and you could solder them all you wanted at really high temperature, and you didn't really have any problems. Okay, so let's analyze a slightly more complicated circuit. This one will have a battery in it along with a capacitor and a resistor. Kirchhoff's law gives us that the voltage of the battery minus the voltage across the capacitor minus the voltage across the resistor must add up to 0. Battery, capacitor, resistor. Let's think about this intuitively for a moment. Basically, the battery is going to push current through this circuit and thereby charge up the capacitor. Now the resistor is going to provide some resistance, so that won't happen instantaneously. Now initially, if the capacitor starts with 0 voltage, then VC is 0, and we just get that the voltage across the battery is equal to IR. In other words, we get just the usual circuit with a battery and a resistor, and V is equal to IR. So initially, when the capacitor is not charged up, the battery will just push current through the circuit, and it will start charging up the capacitor, and the rate at which that current flows is equal to the is given by Ohm's law. Now, as the capacitor starts to charge up, VC becomes non-zero, and the more VC grows, the less IR is, the less the voltage across the resistor, in order to keep Kirchhoff's law satisfied. So as VC grows, the current will actually decrease, because as this voltage across the resistor decreases, that means the current has to decrease. The resistance isn't changing. So as the capacitor charges up, the current becomes less and less. After a long time has gone by, the capacitor will be fully charged, so its voltage will be equal to the voltage across the battery, and the current will be zero. Now, I say after a long time has gone by, really what I mean is this is the situation that we asymptotically approach. Okay, so now, instead of the capacitor gradually discharging and asymptotically approaching zero voltage, it's being gradually charged up by the battery, assuming it starts from zero initial voltage. It's being gradually charged up by the battery until it reaches a voltage equal to the battery's voltage, and then there's no more current anymore. So that's the situation we're asymptotically approaching. In an equation, we would say that the difference between the voltage across the capacitor and the battery, the difference between those voltages is the thing that exponentially decays from some initial value. So V0 here, V0 would be the initial voltage across the capacitor. V0 minus B is the initial difference in their voltages, and that is going to exponentially decay and gradually approach zero. So let's consider a case where the initial voltage across the capacitor is zero, and let's recap what happens. Initially, the voltage across the capacitor is zero, and this means that it drops out of Kirchhoff's law, and what's left is VB equals IR. In other words, we just get Ohm's law. The circuit looks really as if there's no capacitor. Current flows through the circuits. Now, it's accumulating in the capacitor. Positive charges here and negative charges are accumulating here. But at the very first instant when the voltage across the capacitor is zero, the rate at which that current flows is exactly what it would be if there was no capacitor. But immediately the capacitor starts charging up. Okay, this voltage difference exponentially decays. In other words, the voltage across the capacitor exponentially approaches the value of the voltage of the battery. So if we take this equation and we put in that V0 is 0, and we move VB over to the other side, what we find then is that the voltage across the capacitor takes this form. Basically, initially, when t is 0, this is just 1, and we get VB minus VB. Okay, good. So initially, the voltage across the capacitor is 0. But then, as time goes on, this term decays. And once enough time passes, that term is completely negligible, and what we have left is just that the voltage across the capacitor becomes the voltage across the battery. So it's like the old RC circuit that we did. The only real difference is that now we have this battery, and instead of the capacitor exponentially approaching zero voltage, it exponentially approaches the voltage across the battery. Note, by the way, that as before, lambda is equal to 1 over RC. So we can make this a sample problem and say what is the voltage and current at t equals 0, t equals 0.1 seconds, and t equals 1 full second. Well, we already know that Vc initial is just 0, and the current is going to be 9 volts over 1 kiloohm, which gives 9 milliamps. Now, in the second case, we get that we can just apply this equation. All right, and the voltage, well, the lambda, the decay constant, it turns out, is exactly 1 over 0.1 seconds. So we have 0.1 seconds over 0.1 seconds with a minus sign, and that's just minus 1. So we get 9 minus 9 times e to the minus 1, and I find that that's 5.7 volts. The current, then, we can solve for using Kirchhoff's law. And what I find is it turns out to be 9 milliamps times e to the minus 1, or 3.3 milliamps. Sorry about the small writing. After a bunch of time goes by, so in this expression I've just taken the 9 and factored it out. The time is now 10 times more than 1 over the decay constant, so we get e to the minus 10. And that is, I usually round to two significant figures, so the the difference between that and 9 volts is way down several significant figures. So that's basically 9.0 volts. Well, it is 9.0 volts to 2 significant figure accuracy. So the capacitor is basically fully charged up to equal the battery voltage. The current then turns out to be really small at this point, 4.1 microamps. Several 3 orders of magnitude, about basically 1,000 times smaller than it was before. So what's happening now is that the battery has fully charged the capacitor, and the current is very, very, very tiny. Okay, there's just a tiny little bit of current because this is all exponential, so it only exponentially approaches zero, asymptotically approaches zero. It never gets to be complete zero, but that's why it's really tiny, and this is very close to just being the battery voltage now. Okay, for homework, second problem, similar circuit, just different values, and how long does it take the capacitor to reach 90% of the battery voltage?